Welcome. Today we're going to break down a really crucial topic for any engineer. How do you use just a small bit of data, a few samples, to make huge decisions with real confidence? We're going to walk through the main ideas behind statistical estimation, starting with a simple guess and building up to a much more powerful way of understanding our data.
So, let's kick things off with a classic environmental engineering problem. Imagine this. You've got a potential new filter that could be a game changer, but it costs a fortune, and you can only run a few tests on it. So how on earth do you justify that expense? This is exactly where statistical estimation isn't just theory. It becomes one of the most valuable tools you've got.
You know, the heart of all this is something called statistical inference. And it's actually a pretty simple idea. Think about it. We can't test every single drop of water in a reservoir, right? That's impossible. So instead, we take a small, manageable sample. And statistical inference is just the science of using what we learn from that small sample to make really good, reliable conclusions about the entire system, what we call the population.
Because in the real world, no process is perfectly steady. It doesn't matter if you're looking at a chemical reaction, water flowing through a pipe, or cars at an intersection. There's always going to be some natural variation, a little bit of wobble or noise. Our job as engineers is to use stats to see through that noise and figure out what's actually going on underneath.
Okay, so the simplest, most direct way to estimate something is with what we call a point estimate. Honestly, just think of it as your single best guess for some unknown value based entirely on the sample data you've managed to collect.
It's kind of like taking a single snapshot to guess what an entire, huge landscape looks like. For instance, if we grab a few water samples and we calculate the average purity level, well, that average right there, that's our point estimate for the purity of all the water running through that system.
And as engineers, we're measuring stuff all the time. We want to know the average performance of a beam, right? So we use the sample mean. We need to know how consistent or stable a manufacturing process is, so we look at the sample variance. And, we often need to know the failure or success rate of a part. That's where the sample proportion comes in handy. For each of these big picture population parameters, we have a simple sample statistic that gives us our best starting guess.
So here's a really crucial point. A good estimator has to be unbiased, and what that means is that it doesn't systematically guess too high or too low. This is absolutely critical in engineering. I mean, a biased estimate could lead you to design a bridge that's always a little too weak. Sure, any single guess might be a little bit off, kind of like not every dart hits the bullseye, but over the long haul, the average of all our guesses will be dead on.
Okay, so let's dig into this a little deeper. A single number, that point estimate, it's a great place to start. But let's be real, it's almost never going to be perfectly exactly right. There's always going to be some error.
And that question right there leads us to a much more powerful and frankly more realistic tool. Instead of just giving one number and calling it a day, what if we could provide a range of plausible values? A range that actually takes into account all that uncertainty we know is there. You know that snapshot analogy? If a point estimate is a single snapshot, then a confidence interval is like having the whole photo album. It gives you a much richer, more complete picture. It gives you a range where we believe the true value is hiding, and it comes with a specific level of confidence that we're right.
All right, let's walk through a quick, practical example so you can see exactly how this works. Let's say a traffic engineer is out there and collects 25 stop times at an intersection. The average from that sample is 13.2 seconds. And for this clean example, let's pretend we just happen to know that the overall process variance is 4.
The whole calculation follows a really clear three-step process. First, we pick our confidence level. 95% is a pretty common standard in engineering and science. That choice determines our critical value, which we can just look up. For 95% confidence, that value is 1.96 from a standard z-table. Then we just plug everything into this formula. Let's break it down. It starts with our best guess, the sample mean, and then we add and subtract a margin of error. And that margin of error is just our critical value times the population standard deviation divided by the square root of our sample size.
Okay, let's actually plug in the numbers from our traffic example. We start with our average, 13.2. We're going to add and subtract our z-score of 1.96, multiplied by the standard deviation. Now the variance was 4, so the standard deviation is the square root of that, which is 2. Then we divide that by the square root of our sample size, 25, which is 5. So that's just 1.96 times 2/5, giving us a margin of error of 0.784. We subtract that from 13.2 for the low end and add it for the high end.
And this right here is the payoff. This just perfectly illustrates the power of what we just did. We're no longer stuck saying,
Our best guess is 13.2 seconds. Nope, we're now making a much stronger statement. We are 95% confident that the true average for all the cars at that intersection falls somewhere in this range. Now that is a much more useful and frankly more honest statement to make.
Now that last example was a little perfect. In the real world, we almost never actually know the true population variance. We have to estimate it from our sample too. And that, you can imagine, adds another layer of uncertainty to our whole calculation. So to account for this, especially when we have small samples, we use a slightly different tool called the t-distribution. It's really similar to the z-distribution, but it has slightly fatter tails, which is a way of saying it accounts for that extra uncertainty.
Okay, so let's bring it all home. We can now take these tools and get back to that original question about the water filters. Because the real power of this stuff doesn't just come from looking at one system in isolation, but from comparing two different things.
So, see, we're not just estimating the performance of the new filter. What we're really estimating is the difference in performance between the new filter and the old one. We want to find a confidence interval for that difference, mu1 minus mu2, and see if that interval is clearly above 0.
Now, when you're comparing two samples, there's one really critical question you have to ask about your setup. Are you comparing two totally separate, unrelated groups? Like filter A running over here and filter B running over there? Those are what we call independent samples. Or are you comparing related measurements, like testing water quality before it goes in a filter and after it comes out of that same filter? That's what we call paired samples. It's a huge distinction because the formulas we use are totally different for each case.
So, why do we go through all this trouble? Why are we building intervals and comparing differences instead of just, looking at the two averages and calling it a day? Well, the answer really gets to the core of what it means to be an engineer.
It's because these tools let us actually put a number on our uncertainty and actively manage risk. They let us make decisions that aren't just based on a gut feeling, but are scientifically defensible with hard data. This is how we go from just saying, yeah, it looks better, to proving it with mathematical rigor. And that is what's absolutely essential for building systems that are reliable, safe, and efficient.
And really, that's the bottom line right there. Because our single best guess is almost certainly not going to be perfect, we need methods like confidence intervals to understand, to quantify, and to communicate the uncertainty that's always there. The real question isn't, are we exactly right? It's, how confident are we in the range our answer falls in?